I guess we'll get started. So today we'll be going over just some programming basics in Python, and then we'll have a bit of a focus on data analysis after that. So we'll use two packages, which are probably the primary packages for data analysis in Python. So the first one is called Numpy, which stands for numerical Python. So just a lot of functions for analyzing and manipulating data. And then Pandas, which is used for analyzing mainly spreadsheet data and visualizing that as well. So these notebooks are mostly from Madeline, who said she heavily borrowed content from Lena and Charles. I only made a few modifications, so most of the credit goes to them. And then especially for some of the NumPy code I included, it was from the Python Data Science Handbook by Jake Vanderplas, which I highly, highly recommend. It's really, really helpful. So the link is just here if you're interested. And I'll be posting this notebook afterwards as well. So let's jump right into some programming basics. So does everyone have a Jupyter notebook open? Yeah? Okay. So put up your hand if you've used Jupyter notebooks before. Okay. Okay, so we can run each cell by holding down Shift and Enter at the same time. So we'll just start with some basics. So in Python, you can simply add numbers together, and you can do a bunch of mathematical operations. So if you want to do an exponent, you just do a double asterisk, so 4 to the power of 2. And similarly to MATLAB, if you include a semicolon at the end of your statement, it suppresses the output. So we run, oh, my cells aren't running, sorry. So yeah, you can see here when you run this cell, there's no output because we put a semicolon. So moving on to variable assignments, so we can assign values to variables and then perform the mathematical operations on the variables. So we assign a equal to 5, and then we can multiply a by 2. If we assign 4 to this other variable called my variable name, we can then subtract the two variables to get 5 minus 4. And variables don't have to hold numerical values. They can hold anything. So we can assign 2 strings. And in Python, you can add strings, but of course, it's not mathematical addition. It's basically concatenating the strings. But here you see, of course, there's no space. So in order to do that, we have to define that we want to add a space in between the 2 strings. So now we get hello space universe. To print the output of a variable, you can use this print function and then put your variable name in brackets. You can also determine the type of the variable, so using this type function. So you can determine whether it's an integer or a string or a list, etc. So here we're printing B, which we set to the string hello, and we can see that its type is a string. We can also assign multiple values to variables. So the first way we can do this is a list. So we can see that we can assign different elements to the list separated by commas, and the whole list is encompassed in square brackets. So they can be different types of items. So we can have integers, we have a string, we have a list within a list. And so we'll just print out what that list looks like. We can append items to the list using this .append, and we'll just add that item onto the end of the list. So see, we just put Toronto right there. We can remove an item that's in the list. So we'll just take out that item. And again, you can add lists together. So in this case, it will just print out the list twice. And then we also have this object called a tuple, which is an immutable list, which means that you can't add or subtract anything to it, and you can't reassign elements. So for instance, we have this tuple here, we're printing it out, and we're trying to change this first value 1 to a 3, and it's not letting us because just one of the properties of tuples is you cannot change their elements. The next thing we can create is called a dictionary. So a dictionary consists of key-value pairs. So it's kind of like a list, but we use these curly brackets instead. And then you again, hi. Yes. Thanks. Is that better? Okay. Okay. So each element consists of a key and a value. So you separate the key value pairs again with a comma, just like in a list. And then the key comes first, and then its value comes after a colon. So here we're making a dictionary of different fruits. So the fruits are the keys, and then their colors are the values. So in order to access the values, we just put the name of the dictionary, and then in square brackets, the name of the key value. And it will print out, the name of the key, and then it will print out the value associated with that key. And the values, the values don't have to be a single item. You can define a key that has a list of items associated with it. So for the apple key, we have 2 values, green and red. And just like lists, the values don't have to be all strings or all integers. You can combine different types. So in this dictionary, we have the ID key, which has an integer value, and we have this questionnaires key, which is associated with a list of strings. Does that all make sense so far? Any questions? Okay. So we can also do comparisons in Python to see if 2 elements are equal. So to check if they're equal, you just use this double equal sign, and it will print out true if it's true and false if it's false. You can see if one value is greater than another. You can even compare strings, and it's case sensitive. So here, when we have the hey with a capital H, it will print out false. So they do have to be exactly the same case for it to print out true. And before, remember, we defined a as being equal to 5. So if we want to see if it's greater than or equal to 2 to the power of 2, we should get true. And indeed we do. Okay, so indexing in Python is a little bit different compared to MATLAB, for those of you who use MATLAB. So the indexing actually starts at 0. So if you want to print out the first element, you have to use this 0 index, and if you use 1, it's going to print out the second element. Oops. I think I forgot to define fruit, so let's just say fruits equals apples, oranges, bananas. And indexing can also be used for strings. It doesn't have to be for a list. So we just make a string, and printing s at index 0 will just print the first letter. You can also use this negative indexing in Python to start counting from the back. So using an index of -1 will just print the last element in the fruits list. This will print the second last element. And you can also get a slice of a string by using the colon here. So this is going to print out element 0 with the index of 0 to the element with the index of your ending value -1. So it's going to print out the 4th element, which remember is associated with an index of 3. So it basically prints out the word this. If you just start with the colon, that's just telling it to start from the beginning up to the 4th element. And then here we're going to print out, so this would be elements number 6 and 7. Oh yes, yeah. So I'll just copy it. So the original string is just, this is a string. Yeah, so here printing out, so this would be the 6th element, which is the I, and then the 7th element, which is the S. And then again, this is just saying print from the beginning up to the 7th element. And then this is telling us to print from the element at index 7, which is actually the 8th element, up to length s, so basically to the end of the string. And you can also print to the end of the string just by using a colon at the end. Any questions? Yeah.
Index the dictionary like this as well?
I believe so. That's a good question. So if we have our dictionary, it's up here. Let's try that. Fruit colors. I think it will say the key and the value. No, you can't.
So dictionaries are unsorted in Python by default, but what you can do is get the keys using the keys method at the end of the dictionary and do two.
Right.
Keys and then pair of parentheses, and then you can wrap that all in the function, which is called list.
Oh, okay. So like this.
So lists are ordered.
Right.
But that will but,
right.
You can use that to iterate through keys and kind of use it like this.
Cool. Thanks. All right, so now we'll move on to if statements. So what if statements are doing is it's basically checking if an expression is true. And if that expression is true, it's going to perform some command. If the statement is not true and you have elif statements, that's like saying else if. So if the first statement is false, it will check the second statement, et cetera, et cetera. If all these statements are not true, it will go to the else statement and perform the else statement. So here we're defining this list of 2 integers. And first we're checking if the type of S2 is a string, then we're checking if it's an integer and then a float. So if it was a string, it would print S2 as a string, etc. But since it's none of these, it's going to print the else statement, which is S2 is not a string, integer, or a float, since it's a list. We can also use for loops to loop over every item in a list or in a string. So in this case, we have to assign a dummy variable, which is only going to be used in the for loop, basically to access every item in the list. So it's saying basically for every item in the list, so for n and nums, this is what we do to check the remainder. So if the remainder of n divided by 2 is 0, the number is even, so print that it's even. If it's not true, print that the number is odd. So here we can see it's just looping over the numbers, checking if it's even or it's odd, and then printing if it's even or odd. And again, for loops can be used for strings as well, not just for lists. So here we're just saying for every character in the string vowels, just print out that character on a new line.
Go back up a little further, yeah, just to see that for me.
And all this is going to be available online after, but for sure, so you can definitely see that after, so don't try. You don't have to catch all of it right now, but yeah, it'll be on.
Did you have a question?
Please, or interchangeably with while. Do you know if you're going to learn that? I was while before in the for.
I wasn't going to go over while. So while, okay. You good?
Yeah.
Okay. Another cool trick in Python that I really like is called list comprehension. So it's basically running a for loop, but only using a single line. And it's when you want to perform the same kind of manipulation on each item in a list. So kind of the general format is you want to alter a thing for everything in a list of things. So an example here is we have a list of colors and we want to perform some manipulation on all of those colors. We want to make a list of light colors. So all we're going to do is append the string light plus a space to each color. So this is our altered thing for thing color in the list of my colors. and it will make this new list called My Light Colors. So that's just kind of a nice little hack for doing for loops all in one line. The next thing we can do in Python is define functions. So they take on this format, def, the name of your function, and then the inputs. You can make a little, it's called a doc string using these triple quotes, which you can access by doing help and then the name of your function. You perform some manipulation on your input and you return the output. So we'll just run this. And we see that as we run help of squares, it shows what's in that doc string, so the input and the output. Then we can run our function, and we can also, since we included that return statement, it will assign the output of the function to whatever variable we define here, which we can then access later. Okay, so now we're going to move on to the two data analysis packages. So the first one is called Numpy. And what you can do when you import packages is, so a lot of like the higher level functions in Python are part of separate packages which you have to import. So you're basically just telling Python what functions you want to be able to access. And it's common to import packages using kind of like a nickname because you have to specify that nickname every time you call a function. So if you have the shorter nickname, it's just like less typing and more efficient. So the common nickname for NumPy is NP. So you just run import NumPy as NP, and it only takes a second, and now you have access to all of the functions in NumPy. And if you ever need help with a function, two helpful things. If you can't remember the name of a function, you can do this tab completion. So you start typing the name of a function, and then you just press tab, and it will show you all the functions that start with whatever you've typed so far. So here we'll just choose mean. If you do shift tab, it will show you a little help doc string. But if you want more detailed help, you can just put a question mark, and when you run this cell, a more detailed document will come up at the bottom to show you exactly what parameters to use, etc. You can just exit out of that. Okay, so the purpose of NumPy is to be able to perform numerical computations on your data. So NumPy uses this object called an array. So what we're going to do here is we're going to make an array and compare it to a list, which is what we were using before. So this np.arange function is just going to make an array. If you just define one number, it will make an array of 0, increasing integers of 1 up to this number minus 1. So it will do 0 from 14. And it's similar to the range function that's just part of like the standard Python. So if we print the array and the list, we can see that they look pretty much the same, except the list, the elements are separated with commas. But if we print the type of each, we can see, of course, that one's a NumPy array, one's a list. So what NumPy allows you to do is when you, for instance, try to perform mathematical operations on it, remember from before, if we tried to like add lists, it would just, if we did list plus list, it would just print out the list twice. Whereas with arrays, it's going to perform that mathematical operation on all the elements in the array. So see here, we're multiplying all the values in the array by 2, whereas for the list, it's just simply printing out the list twice when we do list times 2. Another cool thing we can do with arrays is reshape them. So we just define here, we want to reshape, there's 15 elements in our array, so we need to make sure that the number of rows times the number of columns adds up to the number of elements in the array. So this is going to reshape our array into 5 rows and 3 columns. You can also use functions to define the mean. So the axis is saying whether you want to take the mean across rows or across columns. So axis 1 is for the columns. You can also look at the max value in each column. And you can also easily turn a list into an array if it consists of numbers. All you have to do is np.array and then your list, and then it will turn your list into an array. So we can just print that out as well. Yeah, and now we have an array. We can also use the list comprehensions that we used before to make two-dimensional arrays. So here we're saying for I in the list of 2, 4, and 6, make a new row in your array, which will consist of I up to, well, it's going to be I plus 3 minus 1, so up to I plus 2. Let's see, here we're starting with 2, 4, 6, and then we're going up to I plus 2, so I plus 1 and then I plus 2. And then we can make arrays of zeros using np.zeros. We can define if we want it to be integers or float. And then we just have to define the number of rows and the number of columns. We can do the same thing, making a matrix of ones. Again, just define the rows and columns. There's also this .full function, which you can define your shape, and then it will fill the array with whatever number you define. So here we're going to make a 3 by 3 array of pi. And then we talked about this function before, the arange function, but there's actually 3 arguments you can give it. So it's going to be in the order of your starting number, your stopping number, and the step size. But the stopping number, it's actually going to go up to this number minus 1. So it's going to go from 0 to 19 with a step size of 2. So like since 19 is an odd number, it's only going to go up to 18. And again, that's similar to using the range function. Another function is linspace, which is kind of similar to arange, except you have your start value, your stop value, and the number of values instead of the step size. And in this case, it will go right up to your stopping value. So here we have 11 values ranging from 0 to 20.
These don't need to all be integers, right? They can be floats.
Yeah. Yeah. Yeah, that's right. So I could do like 20.2 and then, yeah. You can create randomly distributed numbers. So if you do np.random.random, it will be uniformly distributed random numbers between 0 and 1. You can also make a normal distribution, except here the size of your array will be the 3rd argument. The first argument is going to be the mean of your distribution. The second argument will be the standard deviation. So here we're going to make an array with a mean of 0, a standard deviation of 1, and we're going to make it fairly large, and then we can just check to make sure that it's not perfect. So the mean is not too far from 0, and the standard deviation is pretty close to 1. You can also make a variable and then check different. Yeah.
The previous one, is there a way to set C for reproducibility in Python?
Yes. I think you just do np dot. Thanks. And yeah. Yeah. So you can set a seed, so then it should be the same every time. Okay, and so you can also check different statistical properties of an array you make. You can either use np.mean of your array, but once you define this array, you can check it more directly by just doing, if we define an array of IQs, we can check its mean, median, max, and min using these functions here. Or we can use the attributes of the array itself, although it doesn't include, for instance, things like median. So we try to get the median this way, and it gives us an error, but we can check the median by doing np.median instead. We can also check the number of dimensions in our array using .ndim, and then the shape of the array and the size of the array. So that's just going to be the number of elements in the array. So we can see we have a 3-dimensional array. It's 3 by 4 by 5, and its size is 60, and that's simply just 3 times 4 times 5. Indexing works the same for arrays as it does for multi-dimensional arrays as it does for one-dimensional arrays. So here we can use a colon to access all the elements in the third dimension for the first element in dimension 1, the first element in dimension 2. We can also change elements in arrays. And just some more indexing functions, which we kind of talked about before. So this will print the first 5 elements right here, all the elements after 5, using 2 colons, and then 2 will print every other element. You could also print every 3rd element, every 4th element, etc. Here we're telling it to print every other element, but we're giving it a starting index, so start at index 3. And again, we can use -1 to count backwards. So this is printing out all elements in reverse. Another helpful thing to know is if you want to copy an array. So if you just simply do x2 equals x, and then you try to change an element of x2, it's also going to change that same element in x. So let's just print out the original x first. So we had x equals 0 to 9. We made x2 equal to x. We changed the first element of x2, and now we're printing x2 and x, and we can see that it also changed the first element in x, which can be annoying sometimes. So what we can do instead is we're just going to define x3 to be the same as this original x from 0 to 9. We're going to do x3.copy to define x4. And now we'll see that when we change the first element of x4, it's not going to change the first element of x3. So that can be pretty helpful. We'll get to pandas in a minute, but just a couple more cool things in Numpy. So we can concatenate arrays. So just putting them together using np.concatenate. You could also use vstack or hstack to stack them either vertically or horizontally. So vstack now makes a separate row with x2, whereas hstack does the same thing as np.concatenate, just concatenating them horizontally. When you do arithmetic in Numpy, it's, as I mentioned before, it's going to apply the operation to all the elements in your array. So here we're going to add 5 to every array. And kind of a longer way of doing it is you can also use np.add, np.multiply, etc. There's this function called floor divide if you want to divide and then round down to the nearest integer. Use np.power for exponents, and np.mod is going to give you the remainder when you divide by this second input. If you want to add all the elements in your array, you can either do np.add_reduce or np.sum. If you want to add all the elements cumulatively, you can do np.add.accumulate. So that's this output here. So the second element is going to be the sum of elements 1 and 2. The third element is going to be the sum of elements 1, 2, and 3, etc. And another cool thing that I really like in Numpy is called broadcasting. So say we have two arrays. A is a 2D identity matrix, and then B is just a vector of 1s. And we want to add A and B together. So instead of having to make our own matrix replicating B 5 times, Python's going to automatically do that for you when you do A plus B. So that's called broadcasting B into A. So now we can see that every element of A has had 1 added to it. And a practical example for this is if you have some data and you want to subtract the mean for each column, say. So we're going to make some data of normally distributed variables, and we have 30 rows and 6 columns. And we're going to take the mean across all the rows, so we'll get 1 value for each column. So we can see that our data has 30 rows and 6 columns, and the mean is just 6 values. And we can just simply do the mean center data is equal to the data minus the data mean, and the data mean is going to be, again, broadcasted. So it's just going to replicate those means across all the rows. And now if we take the mean across all the rows, we can see it's approximately 0, so it worked. Okay, any questions about NumPy before we get into Pandas? Okay, so Pandas is a package for analyzing data that is in a spreadsheet format. And the common nickname for Pandas is PD, so we're going to do import Pandas as PD. And does everyone have, is everyone connected to Wi-Fi? Yeah? Okay. So in order to read in a CSV file, we're going to do pd.readCSV. And there's just 2 example data sets here. So you can either give a URL to the data, or you can give a path to the data if you have it locally. So if you guys just want to take a second to type in these 2 lines so you can analyze the data. I'll just, sorry, the second one's a little long. Does anyone need more time to type that up? Okay, so just run that cell after importing Pandas. And now what you're doing here is creating, these are called data frames. So data and IRS are called data frames now. So if you want to get a preview of the data, you just do the name of your data frame .head and then the number of rows you want to display. So the default is 5, but we can display the first 10. So this first data set is a health data set that shows the total expenditure on health as a percentage of gross domestic product.
Can you just go up so I can see the,
Yeah.
I didn't get the code. Yeah, just the. Like
What
scroll
is index
over.
underscore call? Yeah.
This?
Yeah, it's just that you can see it.
Okay.
Are those necessary?
Sorry?
Are the index header and the coding necessary?
So the header, this is the default option for header. This is necessary to show the countries as like the indices. Yeah.
Okay. What's the coding?
That is, it has something to do with the, what's it called, like the ASCII codes. Or, yeah. I'm not too familiar with that. Is everyone good?
Do you want to use both data sets?
We're going to use both eventually, yeah.
I put the second longer link on the getter, so if you want, I'm gonna put a link to our getter here, and then you can copy and paste that link that they put there, so. Getter.com/UT. Oh, .im, sorry, you're right. .im/UOT coders/study group.
Lobby.
Sorry?
Lobby.
Lobby. If you go there, the most recent like chat is the link that you can use right there. So you can copy paste that right in.
Cool. Okay, yeah. So the data.head, or whatever the name of your data frame is, .head, will give you a little preview of the data. So now we can see we defined, so this index underscore call is just saying take the first column of the data, and those are going to be the names for the indices. If we don't do that, we didn't do that for IRS, so let's take a look at IRS. So now the indices are just integers. So that's what happens if you don't define the index underscore call. Okay, so now if you do your DataFrame.LOC, it's basically defining the location in the data set. First you give the index, in this case our country name, and then the column. So we're going to see the value for the index of Canada for the year 2008. You can also take a slice of the data, so from Canada to Chile from the years 1999 to 2001, and it'll show you the data just for the slice you indicated. So now we're just going to do some quick plots. We'll go into more detailed plotting in a bit for the IRS data set. So using this matplotlib inline command basically just prevents your plots from popping up in a new window. So we'll run that. And then here you're just saying the data for the index Denmark, you want to plot that, and then it's going to plot Canada and India on the same plot. We want to include a legend to show the different countries. So that's what the plot will look like. All right, so now we're going to move on to the IRS data set. This is a pretty commonly used data set in Python for like data analysis tutorials, and they use it in some of their machine learning tutorials as well. So let's just do a preview of that. We can do iris.shape to see the number of rows and the number of columns. If we run iris.columns, we can see the names of the columns. And what we're doing here is indexing. So you just give the name of a column, and it will show you all the data for that column. And we can see that this format looks different than this data frame format, and that's because it's no longer considered a data frame. We call this a series when you just have an index and then the values for one of the columns. We can easily add new columns to the data set. We just have to define the name of the column in square brackets. So here we're just going to multiply the sepal length times 2. And that's our new column. It will be automatically added to the data frame. Yeah. Yeah, so we're just multiplying all the values in this column by 2. And then we can easily drop the column again. I'm using iris.drop. And then we want to reassign it to so that our data frame is still called iris. And then the axis equals 1 just indicates that we're dropping the column instead of a row. We can also see the mean of all the values in a certain column by just defining the column and then doing .mean. Same thing for median. You can also do this across all columns simply by just not defining a column, and it will show you a mean across all the columns. There's also this nice function to give you a statistical summary for all your columns for several measures, so count, mean, median, etc. Across all the different columns, it will just give you this nice little summary data frame. So often what we'll want to do with our data is only analyze a subset of it. So Pandas makes that pretty convenient. So say we want to analyze only one species of flower, then we can just look at the species column and first of all see what different types of species we have in our data set by doing, it will print out all the unique different types of species. So we can see that here. And then we're arbitrarily just going to choose one of them to analyze. And so what this function is going to do is check the species column. and check to see if each row is equal to Setosa. And it's just going to give us a Boolean true or false for each row. And now we can simply use this as indices to choose the data rows that are equal to Setosa in the species column. So we just paste that same thing as indices within the IRS data frame. And that will just make a smaller data frame that only has species equal to Setosa. And now we can do the same kind of computations on this subset of data. So we'll take the mean across all of the columns just for the Setosa flowers. And we can also perform these computations on all of the groups and get these summary measures for each species using what's called the split, apply, combine workflow. So it's going to split the data frame based on some criteria, in this case, the species. It's going to apply a certain computation on it, so in this case, calculating the mean, and then combine them all back together into a summary table. So we do that by using this group by function, which allows us to choose one of the columns, which is a categorical variable. In this case, we only have the 3 different species of flowers, and then calculate the mean for each of those species. So it's going to give us a nice little summary table for each species. These are the means for all the columns. And you can do the same group by dot size to count the number of observations for each group. And so now we'll get into some data visualization. So Pandas works really nicely with Matplotlib and Seabourn, which are, I guess, the 2 main data visualization libraries in Python. So what we're going to do is perform the same function we did before. So the group by species, and then take the mean, and we're going to assign it to this variable called species comparison. And then all we have to do to plot it is do species comparison dot plot, and then define the type of plot we want. So in this case, we want a bar plot. And so now it's going to show us for each of the different species the values for across each of the different columns. But if we want instead the different colors to represent the different species and the columns to be along the x-axis, we just have to transpose our data frame, so basically flip it using this .t, and then do the same command again. And now we have the different columns along the x-axis, and the species are in different colors. So it's kind of easier to compare across the different species this way. So another package that's really cool for plotting is called Seabourn, and it basically just adds additional functionality and new styles, etc., in different types of plots. So the common nickname for Seabourn is SNS. And so first we'll make what's called a swarm plot. So in order to make the swarm plot, we just do SNS.swarmplot, define what we want on the x-axis, define what we want on the y-axis, and define the data frame where these column names are coming from. Yeah, so there we go. So we can see here that the labels are kind of small, and it might be better if we're giving a talk or making a poster to be able to change that. So Seabourn makes that pretty easy using this SNS.set function. We can choose a style. So these are the different styles you can choose from here. And they tried to optimize the ratios of the labels to the size of your plot, depending on if it's for a paper, a notebook, a talk, or a poster. So you can set that. You can also set additional things such as the size of your figure. This right here is called despining. So basically removing the black lines from the right side and the top side of your plot. So we'll set those options and then run the same plotting command. And now we can see that the labels are a lot bigger and it's easier to read. That's the same thing, making a bar plot. And bar plots are pretty common for displaying data, but they don't really show you too much about like the distribution of the data. So a good plot that allows you to get a better sense of your data distribution is called the Violin plot. So that's what that looks like, and it just gives you a better idea of the shape of the data. And you can also easily combine plots in Seabourn by as long as you specify them in the same cell, it's going to plot one on top of the other. So here we're combining the Violin plot we just did with the swarm plot from earlier. So it's plotting all the data points of the swarm plot on top of the Violin plot, which is pretty neat to see all the data points and then the underlying distribution. Okay, so another thing we might want to do is look at correlations between two continuous variables. So here we're going to plot the width and the length, and then the SNS.ln plot is going to fit a regression line to the data. And we can see that it's slightly negative, but one thing we need to consider is that we have these different species in our data set, and maybe that's affecting the regression a bit. So to look at those different relationships in the data, we can set this fit_reg argument to false so it doesn't plot the regression line. And then we can add Q equals species, and that's going to plot a different color for each of the species. Now we can see that the data are fairly clustered. And now if we add the regression line back in, as long as we keep the hue equals species in there, it's going to fit a regression and set regression to true. It's going to fit a regression line for each of the species. So now they're all positive. And another thing that's pretty cool is this SNS.pairPlot is going to make a plot for each combination of columns. So it's going to make a little two-dimensional grid for each pair of variables. So sepal length. So on the diagonal, it's going to be each variable with itself. So it's only going to plot a histogram. But then for the other variables, it's going to plot a scatter plot. So sepal length versus the width, and then all the different combinations of the columns. So that's a nice way to summarize all the different relationships in your data. Okay, so the last thing we're going to do, sorry I'm going a bit over time, is for more complex visualizations, Seabourn prefers this format called tidy format. So it's basically taking all the columns of your data and just stacking them. So you're going to have basically your variable name in one column, which lists all the different column names, and then we'll show you the index and then the value for each index at each variable. So we can turn our data frame into this tidy format using pd.melt, and anything defined with ID_vars, it's essentially going to keep its own column. So we'll call that iris_long, and you can see that it keeps species as its own column, but all the other variables are stacked. So we have the length for each of the indices, and then all the way down to the width, again, for each of the indices.
So maybe since it's 7, we can take try to wrap it up a bit. And yeah, we'll definitely make sure this is all aligned. And for at least the Seabourn stuff, we actually have a whole lesson dedicated to Seabourn, as you know. So if you want to learn a bit more about the plotting in Matplotlib and Seabourn, there'll be a whole lesson dedicated to that. So this was kind of just like a really brief overview of like the different things you can do.
Yeah. I just have 2 more cells, so sorry for going over time. Okay, so now we can do the plots for all the different variables at once now that we have our data in our long format. So we're just going to set a couple more style things like we did before, but changing the style a bit. You can always play around with this just to see what looks best for your different plots. And now we're going to make a swarm plot with all the different variables on the x-axis and their values on the y-axis. Again, separate them by the species. And this Dodge option, what it's going to do is just make sure that the data points are separated so that they're not overlapping with each other within each variable name. So if we run that, we'll get a plot for all the different column names, all on the same plot, separated by species. And then similar, same as before, we can use two different plots at once, again, using this melted format with the variable on the y-axis and the values on the x-axis, again, separated by species. So yeah, just another nice way of visualizing two different plots at the same time. Yeah, and so that's it for all the demos, and there's just some links to some more resources to help you learn more about Pandas and Seabourn. And again, I'd highly recommend that Data Science Cookbook by Jake Vanderplas. So yeah, thanks guys.